So first of all, I would like to thank the organizing committee for inviting me. I'm Professor Veronica Ambrogi from the Department of Chemical Materials and Production Engineering. And in my talk of today, I will speak about a particular class of functional polymers, which are stimuli-responsive polymers, with a particular focus on the approaches used to design and synthesize a stimuli-responsive polymer in a view of applying them for advanced applications. So, which is our starting point? Our starting point is, of course, nature, because living systems can respond naturally to the varying environmental conditions. So they can adapt their structure and their functionality to suit the changes using a complex system of sensing, adapting, and feedback control system. So for a polymer scientist, the nature is a good starting point, also because in the last years, it is possible to characterize in deep the natural materials and to understand which are the relationship between the structures and their function in a way, with the aim of reproducing them in the labs. So the point is that nature is very simple, but it's very complex because usually natural materials have the ability to respond to multiple triggers and to work as a multifunctional materials. And they have a dynamic response to stimuli. They can self-heal, and they have they are characterized by a particular structure at a molecular level. Now we can understand in deep, we can analyze in deep the structure of natural materials, and we can try to reproduce. For example, one of the most known example is the lotus leaf, which has super hydrophobic and self-cleaning properties. By observing lotus leaf with electron microscopy, we can find that it is characterized by a hierarchical complex structure consisting in microscopic bumps covered by nanostructures that in turn are covered by hydrophobic tails. So in a lab, it is possible to reproduce this structure and to obtain a superhydrophobic surface. Which is the approach that usually we use to synthesize advanced materials? I would say it is a circular approach because somehow we start from the application. And if we want to get a particular function for a particular application, we must design at a molecular level our material. So what we do, we synthesize a material with a particular structure, not only a particular chemical structure, but also a complex structure. And we characterize the material to get all the information about its functionalities, its properties, from the thermal to the mechanical to the functional properties. And this step is very important, not only to characterize the material, but also to improve the synthetic protocol, to have a perfect, not perfect, but an optimized material. So once we get the materials, we are sure that the properties fits with the potential application, we can close somehow our circle. So the design to application is a principle that we usually apply for the synthesis of the advanced materials, for in particular for stimuli-responsive materials. Why polymers? Polymers because I've been working with polymers for 20 years, and I'm convinced that polymers have great potential to be used for advanced materials, as demonstrated by literature and not only by literature. Polymers are usually quite cheap. They're very easy, in some cases, to be produced and modified. They are very resistant. They are thermal resistant, they are mechanical resistant, they are chemically resistant. And they are very versatile because they can be obtained in different topologies, shape, morphologies, and so on. For example, in this sketch, you can see that we can obtain linear polymers, we can obtain star polymers, branched polymers, dendritic polymers. We can use them to functionalize surfaces. We can also obtain them in form of 3D networks, depending on the specific application we want to apply them for. So what are the approaches? As you may know, there are two main approaches, the one which is indicated as top-down or macroengineering approach, and the other which is a bottom-up or molecular engineering. It is a different way to obtain a functional materials, of course. The first is like a sculpture. We start from the bulk polymer, and then we can define the details. We can functionalize it, we can modify it, especially on the surface. With the bottom-up techniques, we start from the molecules, from the atoms, and we can build up our polymers depending on the final properties needed. So we can say that the bottom-up approach is a chemical approach because we follow a path that goes from the molecular to the macroscopic domain, while the top-down approach is more physical, let's say. In the polymer science, there's no good approach, of course. It depends in particular on the costs, on the type of materials or final material we want to get. It depends on many reasons, but we can follow two different approaches. How can we design and synthesize polymers without design structures? There are many methods. Let's start from the conventional one. When we synthesize polymers, we start from monomer. We start from low molecular weight molecules. By the use of an initiator, we activate the monomer and we make it react with other monomers to obtain the macromolecular chains. This is a way to obtain system in which properties are polydispersed. Molecular weight is not one molecular weight, is distributed under a Gaussian curve. If we want to control the molecular weight of the polymers and thus the properties, the final properties of it, we must use, for example, controlled polymerization, which is based on the use of particular reagents, named the dormant reagent, which are able to make the polymerization reaction controlled. In this way, upon the polymerization reaction, we can get macromolecules with the same molecular weight and with controlled structure. For example, we can obtain copolymers in which the moieties are controlled in their chemical structure, in their dimension. We can obtain star polymers. We can obtain all the complex architectures in a polymeric material. So depending again on the final application, we can use a controlled polymerization to get the right system. Another way let's say, more traditional is the polymer modification. It's not really easy as it seems in this slide, of course. It can follow two different paths. One is based on the modification of the monomer. Then the modified monomer is used for the polymerization. The other one, which is more recent, is based on a post-polymerization modification, which can be done, operated also in a localized way. And it enables the obtainment of functional polymers or polymers with particular properties. Another approach, which is more sophisticated, is based on the soft chemistry principle. Basically, two components can recognize through molecular recognition. It means that they are functionalized with a specific chemical group that can interact with non-covalent bonds. Thanks to their interaction as supermolecule forms that is characterized by new functions. It is interesting in this case because depending on the conditions used to assemble these components, you can get different morphologies, different materials with completely different properties as sketched in these slides. This is a good approach, especially for functional polymers. Another approach which is used for mainly for a structural application, but also for functional polymers, is given by the fabrication of nanocomposite. This means that we use a polymeric matrix, and we incorporate inside the polymeric matrix particles which are sensitive to a specific stimulus. So, for example, usually polymers are dielectric. By introducing particles which are sensitive to electrical fields, we can obtain conductive materials. Another approach, interesting approach, I would say, is the obtained on multi-layered structure. We can use different polymers or different materials in form of layers, and we can build up a complex structure with specific properties. So, going into the specific field of stimuli-responsive polymers, what we can do is to select the chemical, the molecular moieties that are able to respond to an external stimulus, and incorporate, according to the protocols that I've shown you before, incorporate them into a polymeric chains in order to obtain a stimuli-responsive polymer. There are, of course, different stimuli. A stimuli-responsive polymer can be sensitive to one or more external trigger. And in this way, we can obtain a single stimuli or multi-stimuli responsive system. If the polymer reacts to the external stimulus by changing physical properties, we can, one or more physical property, we can obtain smart polymers. For example, if we change the temperature because we are in presence of molecular moieties sensitive to temperature variation, if the polymer changes its color, we can obtain thermochromic systems. Again, if we change temperature and it changes its size and volume, we can obtain reversibly, we can obtain shape memory material, and so on. So we can design our system depending on the stimulus we want it to be sensitive to, and depending on the response we want that for our system. And here I show some examples on how a polymer scientist can tailor the properties of the polymers to make them sensitive to a precise stimulus. For example, in this case, we have pH-sensitive polymers. These are polymers which are solubilized in a solvent, typically is water, and they are designed and synthesized in a way to be sensitive to pH variation. So we can introduce into the chain acid groups, base groups, or zwitterionic groups, and depending on the way they are introduced into the polymeric chain, remember, we can also control the growth of the polymer chains by using an exact number of repeating units containing the sensitive groups. We can realize different systems with varying response. Usually the mechanism is the one sketched here. They go from an expanded state to a folded state depending on the pH. So they, for example, can be used for drug delivery. Another system, stimuli-responsive polymers are another class, are thermoresponsive polymers. This can be used both in solution or in a bulk state. For example, if they are introduced into a water solution, they can go from an expanded state to a folded state, depending on their solubility into water at a precise temperature value. So macroscopically, we can see that they change, the solution change from transparent to a cloudy state, and correspondingly, we have these two different arrangements of the chains. And also this system, for example, can be used for drug delivery. Another way to use temperature as a stimuli is in the case of the shape memory polymers. They are obtained in an original shape, but if we heat this polymer with the formate and we cool it again, it can be fixed in a temporary shape, which is stable, until we solicitate the material with an increasing of temperature. By increasing the temperature, the material recovers its original shape. This transition is reversible, can be induced mainly by the temperature, but also by other external stimulus. In a view of designing this material, how can we do? We need a stable network, so processing can be chemical, physical, can be a crystallization state. And we also need a part which is able to react reversible to the external transition, the external stimulus. If we combine these two parts, we can obtain a system, a polymeric system, which is able to use the temperature as a trigger for thermoactuation. So to make a shape memory effect. For example, in our lab, we have synthesized an elastomer starting from a liquid crystalline monomer and using an aliphatic curing agent. So the system was elastomeric. This means that it possessed a sufficient mobility, molecular mobility to rotate in correspondence to the transition of the liquid crystalline state. So in correspondence of the liquid crystalline to the isotropic transition, we could get thermoactuation. Thermoactuation could be improved, for example, by changing the rigid moiety incorporated into the main chain of the elastomer, or by changing the curing agent. If we think about the design of the material and the optimization by characterizing it through an iterative process from the synthesis to the characterization and from the characterization to the synthesis, we could optimize the response of our material. And we could also improve the response by introducing carbon nanotubes, for example. This is another approach I've talked you about. We could enhance the response to the thermal actuation, but we could also make our system sensitive to an external electrical fields because by introducing the carbon nanotubes at a selected percentage, we could reach the percolative threshold up to the material was conductive. So also, in this case, we could easily activate our systems with another stimulus. And in this case, the same system was enhanced in its response by using another polymeric layer, by combining two polymeric layers, one made of a liquid crystalline elastomer and the other one based on a glassy thermoset. We could improve the thermoactuation, make these systems autonomous in its shape memory effect. It moved only through a variation of temperature without the need of an external stress. And going to photoresponsive polymers, of course, also in this case, it's possible to design photoresponsive polymers by incorporating into the main chain, not into the main chain, into the chain of the polymers, segments, molecular segments, which are sensitive to light. Azobenzene is one of the most used because it's one of the most effective in responding to the radiation, but we have a plethora of molecules that can be used to make our polymers sensitive to photoradiation. Here I want to spend a few words on the way we can design the material in order to bias its response to the external stimulus. For example, in the past few years, we have synthesized photoresponsive polymer nanocapsules in which the polymer shell was light sensitive. So by radiating nanocapsules, we could release the active molecules contained into the nanocapsule. So the design of the polymer shell was based on this choice. We used azobenzene moieties to make it sensitive to light. We used a flexible spacer, which is necessary to make to guarantee the molecular mobility to the polymer, and we also used a small amount of cross-linking agent to make it self-standing. Otherwise, it's less mechanically resistant. So by this design, we could synthesize our nanocapsules and make them effective in the release of the drug. But we could also change the response of nanocapsules by modifying the monomers. I told you before, by simply functionalizing the azobenzene moiety with methoxy group, we could shift the response from UV to visible light, and we could effectively use them also for the visible light-induced drug release, especially for some specific wavelength. This is to say that it is possible to bias the properties and thus the function for a specific application by working on the synthesis protocols. So I would like to thank you for your attention. I hope to be to having been in time.